Roughly 9 billion years after the Big Bang, a silent cloud of gas and dust drifted across the galaxy. Cold, unassuming, and ancient. But within it stirred a force older still, gravity. This invisible architect began to pull the cloud inward. At first, gently, then violently. The cloud compressed tighter and tighter under its own weight. Pressures surged. Temperatures climbed. Until finally, in a flash of nuclear ignition, a new star was born. The Sun. Its light pierced the blackness of space. Its gravity seized control. And from that moment, the solar system was born. The Sun didn't simply light the sky, it sculpted space itself. The particles left over from its formation didn't just vanish. Some coalesced into planets, moons, asteroids, and comets. Others formed swirling belts and distant clouds. From this chaotic debris, order gradually emerged. What we now know as our solar system. But this isn't just a group of wandering planets. It's a vast and dynamic domain, a gravitational symphony, stretching billions of kilometers in every direction. The solar system is structured, layered, and active, constantly evolving under the Sun's influence. Its boundaries are not marked by fences or borders, but by energy. The Sun's magnetic field and solar wind define its outer edges, a frontier known as the heliopause, where solar influence fades into the interstellar medium. Let's step back and look at this immense realm. At its core, of course, is the Sun, a blazing sphere of plasma, 1.4 million kilometers in diameter, containing 99.8% of all the mass in the solar system. Its energy fuels the climates of the planets, stirs their atmospheres, and bathes their moons in light and heat. Around it orbit the 8 primary planets, from tiny, sun-scorched Mercury to gas giant Neptune. Each follows an elliptical path governed by Newton's laws, subtly perturbed by gravitational interactions. Between these planets lie countless mysteries. The asteroid belt between Mars and Jupiter, filled with rocky remnants of a failed planet. The gas giants beyond, with their rings and moons, some of which, like Europa or Enceladus, may harbor oceans beneath icy crusts, and possibly life. Further still is the Kuiper Belt, a donut-shaped region filled with icy objects and dwarf planets like Pluto. And even beyond that lies the mysterious Oort cloud, a hypothetical shell of icy bodies surrounding the solar system at distances unimaginable. The solar system is not static. It changes constantly. The Sun pulses with activity, releasing storms of charged particles in coronal mass ejections. These solar events can disturb planetary magnetospheres, power auroras, and even threaten technology on Earth. Every year, new objects are discovered in this cosmic backyard. Dwarf planets, Trojans, trans-Neptunian objects, reshaping our understanding of how the system formed and continues to evolve. If you gathered everything in the solar system except the Sun, all the planets, moons, rocks, gas, dust, and comets, and placed them together, they would still only make up about 0.2% of the system's mass. The Sun is the master of this domain. Its gravity, the puppet master of everything else. Imagine watching this structure unfold in slow motion, the birth of worlds, the dance of orbits, the push and pull of unseen forces. A cosmic ballet choreographed over billions of years. And yet, despite how much we know, the solar system remains full of unanswered questions. What lies beyond the heliopause? Is Planet 9 real? Could life exist on Titan or beneath Europa's frozen crust? Each answer leads to more questions. Each mission, whether it's Voyager, Cassini, New Horizons, or the upcoming Europa Clipper, peels back another layer of the story. And we, from our small blue planet, are witnesses to it all. This isn't just astronomy. This is a story of violence and balance, of chaos and creation, of suns and shadows. And it all began in that cold, silent cloud of gas, pulled inward by gravity's patient hand. The planets of our solar system tell an astonishing story of diversity and extremes. From scorched, airless rocks to storm-ravaged gas giants, each world is a unique chapter in the tale of cosmic evolution. Let's begin closest to the Sun, Mercury. A barren world only slightly larger than Earth's moon, Mercury has no atmosphere to speak of. Daytime temperatures soar to over 430 degrees, 800 degrees, while at night they plunge to 180 degrees, 290 degrees. Its surface is scarred by craters and ancient lava flows, a silent record of billions of years of impacts and volcanic activity. Next is Venus, Earth's twisted twin. Similar in size but radically different in character, Venus is a hellish world where clouds of sulfuric acid swirl in a super-dense atmosphere. The surface pressure is 92 times that of Earth, enough to crush a submarine. And temperatures are hot enough to melt lead, making Venus the hottest planet in the solar system. Its slow rotation and runaway greenhouse effect make it a warning sign of what unchecked atmospheric change can do. Then we arrive at Earth, our home, the only known planet to harbor life. Earth's perfect balance of temperature, atmosphere, magnetic shielding, and water makes it a cosmic rarity. Its dynamic tectonic plates, protective ozone layer, and complex ecosystems are the result of billions of years of geological and biological interplay. And yet, it's fragile, a fact that space exploration has emphasized time and again. Just beyond is Mars, the red planet. Cold, dry, but once flowing with water, Mars intrigues scientists with evidence of ancient rivers, lakes, and perhaps oceans. Vast volcanoes like Olympus Mons and deep canyons like Valles Marineris hint at a violent geologic past. Today, robotic explorers like Perseverance and Curiosity search for signs of ancient life and test technologies that might one day support human colonization. Now we cross the asteroid belt, a region teeming with rocky remnants from the solar system's formation. This zone separates the inner terrestrial planets from the outer gas and ice giants. Jupiter is our next stop, the largest planet in the solar system. A behemoth of gas and storms, Jupiter is over 11 times wider than Earth. Its atmosphere rages with cyclones and tempests, including the Great Red Spot, a storm larger than our entire planet. Beneath its clouds may lie a metallic hydrogen ocean, and at its core, a rocky mass. Jupiter also guards a vast entourage of moons, over 90 and counting, some of which, like Europa, may contain subsurface oceans and hold potential for extraterrestrial life. Saturn follows, the jewel of the solar system, famed for its stunning ring system. These rings are made of ice and rock particles, orbiting the planet in shimmering bands. Saturn is less dense than water. If you could find a bathtub big enough, it would float. Like Jupiter, it's a gas giant with dozens of moons. Among them, Titan stands out, a world with thick orange atmosphere and liquid methane lakes. Titan may possess the chemistry needed for exotic forms of life. Next is Uranus, the first planet discovered with a telescope. This ice giant is tipped on its side, likely due to a massive collision in its past. Its pale blue color comes from methane in its atmosphere. Temperatures on Uranus are among the coldest in the solar system, plunging to 224 degrees, 371 degrees. It has a faint ring system and at least 27 moons, many named after Shakespearean characters. Neptune is last among the major planets. Similar to Uranus in size and composition, it's a dynamic world of deep blue hues and supersonic winds, the fastest in the solar system. Neptune's moon Triton is especially intriguing, with geysers that spew nitrogen and signs of a geologically active surface. Beyond Neptune lies the Kuiper Belt, a realm of icy bodies and dwarf planets. Pluto, once considered the ninth planet, resides here. Though reclassified, Pluto is far from forgotten. Its heart-shaped glacier, towering mountains, and thin atmosphere captured imaginations when NASA's New Horizons spacecraft flew by in 2015. This mission revealed a world far more complex and dynamic than ever expected. These planetary bodies, diverse in form and function, highlight the creativity of cosmic processes. Each offers a different lens on how planetary systems form and evolve. Their variety isn't chaos. It's the result of initial conditions, location from the sun, chemical makeup, and time. But more than just curiosities, these worlds provide context. They help us understand Earth better, why it supports life, how its atmosphere stays stable, what threats exist, both internal and external. The more we learn about the other planets, the more we learn about ourselves. And we realize Earth is not the center of the universe. It's part of an extraordinary family. Infinity. Beyond brings you this journey through our planetary neighborhood, not just to inform, but to inspire. Because somewhere out there, maybe on a moon of Jupiter or under the ice of Neptune's moon, might lie another story just beginning. Stay curious, stay cosmic. Between the orbits of Mars and Jupiter lies a vast and mysterious region known as the asteroid belt. To the casual observer, it might seem empty space, but it's a crowded, dynamic arena filled with rocky remnants from the early solar system, fragments that never coalesced into a planet. Astronomers believe that gravitational interference from massive Jupiter prevented these materials from forming a world. Instead, they remain scattered, some as small as pebbles, others hundreds of kilometers wide. The largest, Ceres, is considered a dwarf planet and holds secrets beneath its surface, possibly including subsurface water ice. The asteroid belt acts like a cosmic museum, preserving clues to how planets form and evolve. These objects are ancient, older than Earth, and studying them gives us a glimpse into the solar system's infancy. But the asteroid belt isn't the only place where relics of the past lie waiting. Beyond Neptune, in the cold, dark outer reaches, is the Kuiper belt, a vast disk of icy bodies orbiting the Sun. This region is home to Pluto, the most famous of the dwarf planets. Once counted among the major planets, Pluto was reclassified in 2006 by the International Astronomical Union. But that change didn't lessen its importance. In fact, it heightened interest. When NASA's New Horizons spacecraft flew by Pluto in 2015, it revealed a world more complex than anyone imagined. Smooth plains of nitrogen ice, towering ice mountains, haze-layered skies. Pluto is alive with geologic activity. Its heart-shaped Tombaugh Regio is iconic, a symbol of how even distant, frozen worlds can be surprisingly dynamic. Nearby lies Haumea, an elongated dwarf planet with a ring system, the only one of its kind discovered so far. There's Makemake, bright and cold, with a thin atmosphere, and Eris, nearly the size of Pluto but even more distant, with an icy surface that reflects nearly all sunlight that strikes it. These dwarf planets, along with thousands of smaller bodies, form the icy frontier of our solar system. Collectively, they challenge what we thought we knew. They blur the line between planet and asteroid, between moon and world. Farther still, perhaps 1,000 times more distant than Pluto, lies a theorized realm called the Oort cloud. Though we've never directly observed it, astronomers believe this spherical shell of icy bodies surrounds the entire solar system, extending almost a quarter of the way to the nearest star. The Oort cloud may be the birthplace of long-period comets, icy travelers that take thousands of years to complete a single orbit. When disturbed, perhaps by a passing star or galactic tide, these objects fall toward the Sun, forming the brilliant tails we see in our skies. Comets are more than just beautiful, they are cosmic messengers. Their ice contains organic molecules, the building blocks of life. Some scientists believe that comets may have helped seed Earth with water and carbon-based compounds during the planet's early formation. The study of these small, distant worlds opens up enormous scientific opportunities. They offer hints at the solar system's formation, its chaotic early years, and the possibility that life-sparking ingredients may be more common than we ever imagined. But these areas also raise profound questions. Could there be a yet undiscovered planet, a Planet 9, lurking in the darkness beyond the Kuiper Belt? Some astronomers point to the strange orbits of several trans-Neptunian objects as possible evidence. If such a planet exists, it might be several times the mass of Earth and take tens of thousands of years to orbit the Sun. Its discovery would rewrite textbooks and dramatically expand our understanding of the solar system's architecture. Yet for all we've uncovered, so much remains unknown. The more we look to the edges, the more we realize how vast, varied, and unfinished our knowledge truly is. These minor worlds, asteroids, dwarf planets, and comets, may lack the size of Jupiter or the fame of Mars, but their importance is growing. They are no longer just footnotes in astronomy books. They are frontiers, and they might hold the key to understanding not just where we come from, but where we're going. With every passing mission, telescope, and discovery, Infinity Beyond brings the story of these cosmic wanderers into focus. Stay with us as we continue exploring the frozen secrets at the edge of our sun's influence, because beyond the familiar lies the unknown, and that's where the real adventure begins. Among the most dramatic and unpredictable visitors to our solar system are comets, icy bodies that orbit the sun along long, elliptical paths. For much of their journey, they remain cold and invisible. But when they approach the inner solar system, sunlight warms their surfaces, releasing gases and dust that form glowing comas and long tails stretching millions of kilometers. These glowing wanderers have fascinated humanity for millennia. Ancient civilizations often saw comets as omens, harbingers of change or disaster. Today, we see them as time capsules from the solar system's earliest days. Comets preserve the original ices, dust, and organic materials from the solar nebula, the primordial disk that birthed our sun and planets. Modern science understands comets not as threats, but as keys to understanding cosmic history. Their composition, water ice, carbon compounds, silicates, is a snapshot of the ingredients available when the planets formed. Take Comet 67 Churyumov-Gerasimenko, famously visited by the European Space Agency's Rosetta mission. In 2014, Rosetta became the first spacecraft to orbit a comet, and its lander, Philae, made history by touching down on its surface. The images revealed an alien landscape, jagged cliffs, dust-covered plains, and jets of gas streaming into space. Instruments detected organic molecules, some of the same found in Earth's biology, sparking discussion about life's cosmic origins. But comets are only part of the story. The solar system is full of near-Earth objects, asteroids and comets whose orbits bring them close to our planet. Some are small. Others are large enough to cause regional or even global damage if they were to collide with Earth. The most famous cosmic impact in Earth's history is the one that occurred 66 million years ago, the Chicxulub impact. A massive asteroid or comet struck what is now the Yucatan Peninsula in Mexico, triggering global fires, tsunamis, and a dramatic climate shift. This event likely led to the extinction of 75% of Earth's species, including the non-avian dinosaurs. Impacts have shaped not just Earth, but every body in the solar system. Craters dot the surfaces of the Moon, Mercury, Mars, and countless asteroids. These impacts are reminders of the solar system's violent past, and that space is not static. Today, planetary defense is a growing field of research. Scientists around the world track thousands of near-Earth objects. NASA's DART mission, the Double Asteroid Redirection Test, made history in 2022 by intentionally crashing a spacecraft into the asteroid Dimorphos to alter its trajectory. It was the first real test of our ability to change the path of a celestial object, a step toward protecting Earth from future impacts. These missions underscore a critical truth. Earth does not exist in isolation. It's part of a dynamic solar system where cosmic collisions, while rare, are real. But there's a silver lining. Some scientists believe that without these impacts, life on Earth might never have emerged or survived. Comets may have delivered water and organics to the early Earth. Impacts may have sparked key evolutionary shifts. In this sense, cosmic collisions are not just destructive, they're also creative. They're the engines of change. This understanding reshapes how we see our place in the universe. We are not passive observers, but active participants in a system where the heavens still move and matter. And with tools like telescopes, satellites, and deep space probes, we are more equipped than ever to anticipate, understand, and even mitigate cosmic threats. Yet many questions remain. How often do large comets enter the inner solar system? Are there dark, untracked objects lurking in deep space? Could future impacts be predicted decades in advance? Each new mission helps answer these questions. Future explorations like the Comet Interceptor or enhanced asteroid surveys will deepen our knowledge. At the same time, educational outreach, like what we do here at Infinity Beyond, keeps public awareness growing. Because the more we know, the safer we become. Not just from potential threats, but from the limits of ignorance. Ultimately, the study of comets and cosmic impacts bridges science and storytelling. These icy bodies and fiery collisions are not just data points. They are part of humanity's cosmic saga, reminders that the universe is alive, unpredictable, and astonishingly interconnected. So next time you see a comet blazing across the night sky or read about a crater on Mars, remember, you're witnessing history, ancient, powerful, and still unfolding. The sun is not a quiet ball of light. It's a dynamic, explosive force, the very heart of our solar system. And it has a profound influence on Earth in ways that go far beyond providing daylight and warmth. Welcome to the world of solar flares, coronal mass ejection, CMO, and space weather. Phenomena that not only shape conditions in space, but directly affect life and technology on Earth. At the core of this activity is the sun's magnetic field. Twisting, tangling, and reconfiguring constantly, this magnetic energy sometimes becomes unstable. When it does, it can release massive bursts of radiation and particles into space, what we call solar flares. These flares can be immensely powerful. In mere minutes, they can unleash the energy equivalent of billions of hydrogen bombs. Most solar flares occur in active regions near sunspots, dark patches on the solar surface caused by magnetic disturbances. Occasionally, a solar flare is accompanied by a coronal mass ejection, a massive bubble of solar plasma and magnetic field that is hurled into space. If a CME is aimed toward Earth, it can reach us in a few days and create significant space weather effects. But what exactly is space weather? Unlike Earth's weather, which involves wind, rain, and temperature, space weather is a set of electromagnetic and particle conditions influenced by solar activity. It impacts satellites, power grids, communications, and even the health of astronauts. When a CME slams into Earth's magnetosphere, the magnetic bubble surrounding our planet, it can compress and disturb it. This interaction generates geomagnetic storms, which cause beautiful auroras near the poles, but can also damage electrical systems. In 1989, a powerful geomagnetic storm caused by a CME knocked out power across Quebec, Canada, leaving millions in the dark for hours. In 2003, during the Halloween storms, dozens of satellites were disrupted. airline flights were rerouted, and astronauts on the ISS were warned to seek shelter. The most powerful solar storm ever recorded, the Carrington event of 1859, caused telegraph systems to spark and fail. If a similar event occurred today, with our modern reliance on electronics and global connectivity, it could be catastrophic. That's why monitoring the sun is more important than ever. Organizations like NASA, ESA, and NOAA maintain fleets of space observatories that keep a constant eye on our star. The Solar Dynamics Observatory, SDO, SOHO, and Parker Solar Probe provide real-time data on solar conditions, helping predict solar storms and alert power companies and satellite operators in advance. Understanding space weather isn't just about avoiding disaster. It's also about exploration. As we send humans back to the Moon and eventually to Mars, we must account for the radiation risks posed by solar activity. Unlike Earth, other worlds lack strong magnetic shielding, making astronauts more vulnerable to solar radiation. Even airline crews flying at high altitudes near the poles during a solar storm can receive increased radiation doses. GPS signals can be disrupted. Shortwave radio communications, critical for military and maritime operations, can go dark. And yet, there's beauty in this danger. When solar particles collide with Earth's upper atmosphere, they create the aurora borealis and aurora australis, shimmering curtains of green, red, and purple light dancing across the polar skies. These northern and southern lights are not only spectacular, but living proof that we're constantly interacting with the sun. They're a visual reminder that space is not empty. It's alive. It's connected. The sun operates in cycles, most notably the 11-year solar cycle, which governs the frequency of sunspots and solar storms. We are now entering solar cycle 25, expected to peak around 2025. Scientists anticipate increased solar activity, which could bring both stunning auroras and significant space weather risks. Preparation is key. The more we understand the sun, the better we can predict its behavior. Researchers are developing advanced models to simulate the solar corona and magnetic field. Missions like Parker Solar Probe, which is flying closer to the sun than any spacecraft in history, are revolutionizing our understanding of solar physics. Meanwhile, engineers are hardening satellites against radiation. Airlines are updating flight plans based on space weather forecasts, and power companies are building resilience into their grids. It's a coordinated effort, blending astrophysics, engineering, atmospheric science, and public safety. At Infinity Beyond, we believe knowledge is protection. That's why we share the latest insights into solar activity, geomagnetic forecasts, and what it all means for our future in space. Because ultimately, the sun isn't just out there, it's part of us. Its energy sustains life. Its outbursts shape our skies. Its storms challenge our technology and stretch our understanding. And as we venture farther into the cosmos, the sun will remain both a source of wonder and a force to be reckoned with. The sun is not a quiet ball of light. It's a dynamic, explosive force, the very heart of our solar system. And it has a profound influence on Earth in ways that go far beyond providing daylight and warmth. Welcome to the world of solar flares, coronal mass ejection, CMO, and space weather, phenomena that not only shape conditions in space, but directly affect life and technology on Earth. At the core of this activity is the sun's magnetic field. Twisting, tangling, and reconfiguring constantly, this magnetic energy sometimes becomes unstable. When it does, it can release massive bursts of radiation and particles into space, what we call solar flares. These flares can be immensely powerful. In mere minutes, they can unleash the energy equivalent of billions of hydrogen bombs. Most solar flares occur in active regions near sunspots, dark patches on the solar surface caused by magnetic disturbances. Occasionally, a solar flare is accompanied by a coronal mass ejection, a massive bubble of solar plasma and magnetic field that is hurled into space. If a CME is aimed toward Earth, it can reach us in a few days and create significant space weather effects. But what exactly is space weather? Unlike Earth's weather, which involves wind, rain, and temperature, space weather is a set of electromagnetic and particle conditions influenced by solar activity. It impacts satellites, power grids, communications, and even the health of astronauts. When a CME slams into Earth's magnetosphere, the magnetic bubble surrounding our planet, it can compress and disturb it. This interaction generates geomagnetic storms, which cause beautiful auroras near the poles but can also damage electrical systems. In 1989, a powerful geomagnetic storm caused by a CME knocked out power across Quebec, Canada, leaving millions in the dark for hours. In 2003, during the Halloween storms, dozens of satellites were disrupted. Airline flights were rerouted, and astronauts on the ISS were warned to seek shelter. The most powerful solar storm ever recorded, the Carrington event of 1859, caused telegraph systems to spark and fail. If a similar event occurred today, with our modern reliance on electronics and global connectivity, it could be catastrophic. That's why monitoring the sun is more important than ever. Organizations like NASA, ESA, and NOAA maintain fleets of space observatories that keep a constant eye on our star. The Solar Dynamics Observatory, SDO, SOHO, and Parker Solar Probe provide real-time data on solar conditions, helping predict solar storms and alert power companies and satellite operators in advance. Understanding space weather isn't just about avoiding disaster. It's also about exploration. As we send humans back to the Moon and eventually to Mars, we must account for the radiation risks posed by solar activity. Unlike Earth, other worlds lack strong magnetic shielding, making astronauts more vulnerable to solar radiation. Even airline crews flying at high altitudes near the poles during a solar storm can receive increased radiation doses. GPS signals can be disrupted. Shortwave radio communications, critical for military and maritime operations, can go dark. And yet, there's beauty in this danger. When solar particles collide with Earth's upper atmosphere, they create the aurora borealis and aurora australis, shimmering curtains of green, red, and purple light dancing across the polar skies. These northern and southern lights are not only spectacular, but living proof that we're constantly interacting with the sun. They're a visual reminder that space is not empty. It's alive. It's connected. The sun operates in cycles, most notably the 11-year solar cycle, which governs the frequency of sunspots and solar storms. We are now entering solar cycle 25, expected to peak around 2025. Scientists anticipate increased solar activity, which could bring both stunning auroras and significant space weather risks. Preparation is key. The more we understand the sun, the better we can predict its behavior. Researchers are developing advanced models to simulate the solar corona and magnetic field. Missions like Parker Solar Probe, which is flying closer to the sun than any spacecraft in history, are revolutionizing our understanding of solar physics. Meanwhile, engineers are hardening satellites against radiation. Airlines are updating flight plans based on space weather forecasts, and power companies are building resilience into their grids. It's a coordinated effort, blending astrophysics, engineering, atmospheric science, and public safety. At Infinity Beyond, we believe knowledge is protection. That's why we share the latest insights into solar activity, geomagnetic forecasts, and what it all means for our future in space. Because ultimately, the sun isn't just out there, it's part of us. Its energy sustains life. Its outbursts shape our skies. Its storms challenge our technology and stretch our understanding. And as we venture farther into the cosmos, the sun will remain both a source of wonder and a force to be reckoned with. Imagine a giant invisible bubble surrounding our entire solar system, one that shields us from deadly radiation and the unknowns of interstellar space. This structure exists. It's called the heliosphere, and it may be one of the most important and least understood features in our cosmic neighborhood. The heliosphere is formed by the solar wind, a continuous stream of charged particles emitted by the sun. This wind travels outward in all directions at supersonic speeds, carrying the sun's magnetic field across the solar system. As it expands, it creates a vast protective bubble that separates us from the harsh conditions of interstellar space. Inside this bubble, the solar wind dominates. Outside it, the space between stars is filled with cosmic rays, magnetic fields, and matter expelled by distant supernovae. The boundary where the solar wind slows down and begins to interact with this interstellar medium is called the termination shock. Beyond that lies the helios sheath, a turbulent region where solar wind and interstellar material mix. The very edge of the heliosphere, where the solar wind's strength can no longer push back against the interstellar medium, is known as the heliopause. This is the true outer boundary of our solar system's influence. Beyond it lies interstellar space. Two spacecraft have crossed this boundary, Voyager 1 and Voyager 2. Launched in 1977, these pioneering probes have traveled farther than any human-made objects. In 2012 and 2018, respectively, they passed through the heliopause and entered interstellar space, sending back priceless data about the environment beyond. What they've found is astonishing. Outside the heliosphere, the density of particles increases. The temperature shifts. Magnetic fields behave differently. It's like crossing from a warm ocean current into icy open waters. The rules change. Yet, the heliosphere isn't a perfect sphere. It's shaped by the sun's motion through the galaxy, forming a comet-like tail behind it. Some scientists believe it may be more of a croissant shape, pinched at the sides by magnetic pressure. The true shape remains a subject of research and debate. Why does the heliosphere matter? Because it's our first line of defense. Cosmic rays, high-energy particles from supernovae, and other violent galactic events constantly bombard the galaxy. Without the heliosphere, Earth would be exposed to far more of this dangerous radiation. It could damage satellites, harm astronauts, and potentially affect climate and biological evolution. In fact, some researchers believe variations in the heliosphere's strength over time may correlate with past mass extinctions or climate shifts. As the sun moves through different regions of the galaxy, encountering interstellar clouds or denser particle fields, the heliosphere may compress or expand, altering how much cosmic radiation reaches Earth. Studying the heliosphere also helps us understand other stars. If our sun has such a structure, what about other stars with strong solar winds? Might they have their own protective bubbles? If so, these stellar astrospheres could be essential for shielding exoplanets from radiation, a key factor in the search for habitable worlds. And here's where it gets even more exciting. NASA's Interstellar Mapping and Acceleration Probe, IMAP, set to launch soon, will provide a global view of the heliosphere and its boundaries. It will study how solar wind particles are accelerated and how the heliosphere interacts with the galaxy beyond. Other missions, like the Voyager probes, continue to push the frontier, sending back faint whispers from the edge of space. These signals, often no stronger than a cell phone tower's ping, contain clues about our place in the galaxy. On Earth, we're building better models to simulate the heliosphere in 3D. These simulations help us prepare for changes in space weather and understand how the sun's influence extends far beyond the planets. But there's still so much we don't know. How thick is the helios sheath? Does the heliosphere fluctuate in shape or strength with the solar cycle? Could it collapse entirely under certain cosmic conditions? These questions are more than academic. They affect spacecraft design, human exploration, and even the future of interstellar travel. Any probe leaving the solar system must pass through the heliosphere, and understanding that journey is critical. For now, we live comfortably within the heliosphere's shelter. But someday, humanity may venture beyond it. And when we do, we'll be stepping into a realm shaped not by the sun, but by the collective forces of the galaxy. Here at Infinity Beyond, we explore these boundaries not just to inform, but to inspire. Because the edge of the solar system isn't an end, it's a beginning, a gateway to deeper questions, to new discoveries, to the infinite. So next time you look up at the sun, remember, it's not just warming your skin. It's building a cosmic shield, shaping a bubble of safety that stretches billions of kilometers across space. And that shield is our silent guardian, keeping the stars at bay while we gaze toward them with wonder. In 1977, NASA launched 2 spacecraft that would go farther than anything humanity had ever built, Voyager 1 and Voyager 2. What began as a mission to explore the outer planets became something far greater, a journey to the very edge of the solar system and beyond. The Voyager missions were designed during a rare planetary alignment, one that occurs only once every 176 years. This alignment allowed the spacecraft to use gravitational assists from Jupiter, Saturn, Uranus, and Neptune to slingshot their way through the outer solar system with minimal fuel. Voyager 1 launched on September 5, 1977, and Voyager 2 launched a few weeks earlier, on August 20th. Despite the naming, Voyager 1's trajectory took it on a faster path out of the solar system. These spacecraft were packed with scientific instruments, cameras, magnetometers, plasma detectors, and cosmic ray sensors, all designed to study the environments of the outer planets and their moons. Voyager 2 remains the only spacecraft to have visited Uranus and Neptune, revealing the icy blue worlds in unprecedented detail. It discovered new moons, dark rings, and intense magnetic fields, reshaping our understanding of these distant giants. Meanwhile, Voyager 1 made its closest approach to Saturn and Titan, gathering crucial data about the moon's thick atmosphere and strange Earth-like processes. But it wasn't just about science. Each Voyager carries something special, the golden record. Encased in a protective aluminum cover, this phonograph record contains greetings in 55 languages, music from around the world, and images portraying the diversity of life and culture on Earth. It was humanity's message in a bottle, cast into the cosmic ocean in the hope that one day, some intelligent life might find it. As the Voyagers completed their planetary tours, their mission shifted. They became interstellar explorers, traveling into the uncharted region beyond the planets. In 2012, Voyager 1 became the first human-made object to cross the heliopause, the boundary where the solar wind meets the interstellar medium. Voyager 2 followed in 2018. Both spacecraft now drift through interstellar space, sending back faint but priceless signals. They are still powered by radioisotope thermoelectric generators, RTGs, converting heat from plutonium decay into electricity. But their power is slowly fading. NASA expects to begin shutting down instruments one by one to conserve energy, with both craft likely falling silent sometime in the early 2030s. Even when their voices go quiet, the Voyagers will continue to drift, silent ambassadors of Earth. In 40,000 years, Voyager 1 will pass within 1.6 light-years of another star, Gliese 445. And yet, for all their distance, the Voyagers remain connected to us. Every bit of data they send must travel billions of kilometers, taking over 22 hours to reach Earth. And yet, it still arrives. That connection is a triumph of engineering, persistence, and imagination. What have we learned from these missions? We've discovered that the solar system is more dynamic, more diverse, and more complex than we imagined. We've detected new magnetic phenomena, unexpected plasma interactions, and gradients in cosmic ray intensity. We've seen active geysers on Neptune's moon Triton and heard the eerie sounds of interstellar space. But perhaps the greatest legacy of the Voyager program is its symbolism. It shows what humanity can achieve when we reach beyond borders, beyond conflict, and beyond fear. When we explore not for conquest, but for knowledge. Carl Sagan, one of the architects of the Golden Record, famously said, "The spacecraft will be encountered, and the record played only if there are advanced spacefaring civilizations in interstellar space." But the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. Indeed, the Voyager missions remind us that Earth is a pale blue dot, fragile, unique, and deeply connected to the cosmos. They also serve as inspiration for future interstellar exploration. Projects like Breakthrough Starshot, which envisions sending laser-powered microprobes to nearby star systems, owe much to the trail blazed by the Voyagers. And here on Earth, Voyager's story continues to capture imaginations. Books, films, documentaries, and even music have celebrated its odyssey. At Infinity Beyond, we believe stories like Voyager's are more than just space science. They are human stories, stories of persistence, vision, and the endless drive to know more. As these twin explorers continue their lonely journey, they carry with them our dreams, our curiosity, and our hope that we are not alone, because in the darkness between stars, Voyager whispers back, "We were here." Beyond the planets, beyond the icy reaches of the Kuiper Belt, beyond even the heliopause, lies a realm few understand. Interstellar space. It is vast, cold, and ancient, a dark ocean between stars. But what exactly is out there, and how do we know? Thanks to the Voyager spacecraft, which have now entered interstellar space, we're beginning to answer these questions. The environment beyond our solar system is not empty. It's filled with tenuous gas, magnetic fields, and galactic cosmic rays. High-energy particles from exploding stars and distant phenomena. When Voyager 1 crossed the heliopause in 2012, it detected a sudden jump in cosmic ray intensity and a drop in solar particles. Clear indicators it had left the protective bubble of the heliosphere. Voyager 2 confirmed similar patterns in 2018. What they found is astonishing. Interstellar space is not as empty as once believed. Instead, it's a dynamic, turbulent region, shaped by pressure from distant stars, shock waves from supernovae, and the galactic magnetic field. This region is known as the local interstellar cloud, a wispy region of gas and dust that our solar system is currently passing through. Its density is extremely low, far lower than any vacuum created on Earth, but over vast distances, it exerts influence. Cosmic rays from this space pose a radiation hazard to astronauts and electronics. Understanding their behavior is crucial for future interstellar missions, and even for long-duration spaceflight within our solar system. But beyond the local cloud lies even more mystery. Astronomers believe the Sun is traveling through the Milky Way at roughly 828,000 km, orbiting the galactic center once every 225 to 250 million years, a galactic year. As we travel through the galaxy, the heliosphere shifts and adapts, interacting with new interstellar environments. These changes may have impacts on solar wind intensity, Earth's climate, and cosmic radiation levels. Could our solar system one day enter a denser region of space, one with more particles, stronger magnetic fields, or more dangerous cosmic rays? It's possible. Studying these boundaries is now a high priority. NASA's IMAP mission, the Interstellar Mapping and Acceleration Probe, is scheduled to launch soon. Its goal is to map the boundary of the heliosphere, understand how particles are accelerated, and trace the origins of cosmic rays. But reaching deeper into interstellar space will take more than mapping. It will take missions that go far beyond Voyager. That's why researchers are now designing the next generation of interstellar probes. One concept, known as Interstellar Probe, envisions a spacecraft that could travel twice as far as Voyager within 50 years, using solar sails or gravity assists to escape the sun's grasp faster. Such missions could explore the true nature of the interstellar medium, detect hydrogen walls around the heliosphere, and potentially fly past other star systems in the distant future. But even with the best propulsion systems we have today, reaching the nearest star, Proxima Centauri, 4.24 light-years away, would take over 70,000 years. That's why visionary projects like Breakthrough Starshot aim to change the rules. By using powerful ground-based lasers to propel small, ultralight spacecraft at 20% the speed of light, we could potentially reach Proxima in just 20 years. It's an ambitious dream, but so was Voyager once. The question remains, what would we find? The space between stars is not lifeless. It may be filled with rogue planets, worlds flung from their solar systems, wandering in eternal night. It may hide interstellar objects, like Oumuamua, the mysterious traveler that passed through our solar system in 2017. And perhaps it may contain something more, signals, structures, or phenomena that challenge our understanding of the cosmos. After all, interstellar space is not just a destination, it's a canvas, one where the next chapter of human exploration will be written. Here at Infinity Beyond, we believe the edge of the solar system is not an ending, but a beginning, a doorway to the galaxy, a call to push farther, because beyond the known lies the incredible. And in that vast, star-speckled silence, we may yet find our greatest discoveries. For centuries, humanity has looked up at the night sky and asked one profound question: are we alone? The vastness of the universe makes the possibility of extraterrestrial life not just plausible, but statistically likely. With billions of galaxies, each containing billions of stars and potentially trillions of planets, it seems improbable that Earth is the only world where life has emerged. The discovery of exoplanets, planets orbiting stars beyond our Sun, has revolutionized the search for life. Since the first confirmed detection in 1992, scientists have now cataloged over 5,500 exoplanets, with more discovered every week. Some of these worlds are gas giants like Jupiter. Others are rocky, Earth-sized planets orbiting in the habitable zone, the region around a star where liquid water could exist. These Goldilocks planets are prime candidates in the search for life. The James Webb Space Telescope, JWST, is currently at the forefront of this search. With its infrared vision, JWST can analyze the atmospheres of distant exoplanets, searching for biosignatures, chemical traces like oxygen, methane, or water vapor that may indicate biological activity. One such target is TRAPPIST-1, a red dwarf star with at least 7 Earth-sized planets, several of which lie within its habitable zone. These planets may have oceans, atmospheres, and potentially even life. But life doesn't have to look like life on Earth. On our own planet, extremophiles, organisms that thrive in boiling acid, deep-sea vents, and frozen lakes, prove that life can exist in unimaginable conditions. Could similar organisms live beneath the icy shells of Europa or Enceladus, moons of Jupiter and Saturn that may harbor subsurface oceans warmed by tidal heating? NASA's Europa Clipper and ESA's JUICE mission will soon investigate these possibilities, scanning for organic molecules, water plumes, and thermal activity. Meanwhile, the SETI Institute continues to scan the sky for technosignatures, radio signals, or laser bursts that might be intentional transmissions from intelligent civilizations. In 1977, the WOW signal was detected. A powerful, unexplained radio burst from deep space. Though never repeated, it remains one of the most intriguing candidates for alien contact ever recorded. Yet decades of searching have yielded no confirmed signals. This has led scientists to propose the Fermi paradox. If life is common, where is everybody? Possible answers include: civilizations are too far apart in time and space. Intelligent life is rare or self-destructive. Alien signals are too advanced for us to detect. Or perhaps they're watching, but not responding. The Drake equation, developed by Frank Drake in 1961, estimates the number of communicative civilizations in the galaxy based on factors like star formation, planet formation, life development, and technological advancement. Depending on the inputs, the equation yields wildly different results, from 0 to millions. But one thing is clear: the search continues. From sending messages aboard Voyager's Golden Record to targeted radio broadcasts like Arecibo's 1974 transmission, humans have already reached out to the cosmos. Whether anyone is listening remains unknown. More recently, scientists have begun exploring Dyson spheres, alien megastructures, and exoarchaeology, the hunt for large-scale artificial constructs around distant stars. One such case was the mystery of Tabby's star, KIC 8462852, which dimmed irregularly in a way that couldn't be fully explained by planets or dust. Some speculated it could be evidence of alien engineering, though natural explanations remain more likely. The rise of AI and advanced data analysis tools has accelerated the search. Machine learning now helps scan massive data sets for patterns or anomalies humans might miss. Ultimately, whether or not we find life beyond Earth, the journey itself is transforming our understanding of biology, astronomy, and ourselves. And if we do discover extraterrestrial life, whether microbial or intelligent, it would be the most profound discovery in human history. It would challenge our religions, philosophies, and view of our place in the universe. At Infinity Beyond, we believe the cosmos is not silent, only waiting for the right questions. The truth may lie around the next star, beneath Europa's crust, or encoded in signals we have yet to understand. Until then, we keep searching, because to search is to hope, and in the silence of the stars, there may yet be a whisper answering back. Humanity's journey into space has just begun. We've explored the moon, sent probes to every major planet, and even touched the edge of interstellar space with the Voyager missions. But what comes next? What lies beyond the solar system? In the coming decades, the line between science fiction and science fact will begin to blur. New technologies, international collaborations, and a deepening hunger for discovery are pushing the boundaries of what's possible. One of the most anticipated next steps is the return to the moon, not just for brief visits, but to build a sustained human presence. NASA's Artemis program, alongside efforts from Europe, Japan, and private companies like SpaceX and Blue Origin, aims to establish a lunar base. The moon will become a testing ground for technologies and life support systems required for deeper missions. From there, the next great leap is Mars. Long the dream of visionaries, Mars represents our first real opportunity to become a multi-planetary species. Robotic explorers like Perseverance are already scouting landing zones, searching for signs of ancient life, and testing tools to produce oxygen from the Martian atmosphere. SpaceX's Starship, designed for deep space travel, could be the vehicle that finally carries humans to Mars. If successful, it could pave the way for permanent settlements, agriculture, and terraforming experiments on the Red Planet. But even Mars is just the beginning. In the next century, we may begin to send crewed missions to the outer solar system, exploring the icy moons of Jupiter and Saturn, where subsurface oceans may harbor alien life. Nuclear propulsion, cryogenic sleep, and AI-driven navigation may enable voyages lasting decades. Beyond exploration, there's mining the asteroids. These space rocks contain valuable metals like platinum and gold, as well as water, which can be turned into fuel. Entire industries could arise from harvesting the resources of the asteroid belt, creating an off-Earth economy. But the ultimate dream lies in the stars. Reaching the nearest star systems, like Alpha Centauri, remains a massive challenge. Current propulsion systems are far too slow. Voyager 1, humanity's farthest spacecraft, would take over 70,000 years to reach even the closest star. To close this gap, scientists are researching revolutionary propulsion concepts. Light sails, propelled by lasers or sunlight, as proposed by breakthrough Starshot. Nuclear fusion engines, which could generate massive thrust and reduce travel time. Antimatter propulsion, one of the most energy-dense ideas ever conceived. Even wormholes and warp drives, once purely science fiction, are now being studied theoretically within Einstein's framework of relativity. These ideas may seem distant, but so once did flight, space stations, and interplanetary probes. As our understanding deepens, we may even redefine what it means to travel. Could digital consciousness, transmitted as light across space, reach distant worlds faster than any ship? Could AI explorers, seated with human knowledge, become our first ambassadors to the galaxy? Yet, exploration is not just about distance, it's about understanding. New telescopes like the James Webb and future observatories will peer into the atmospheres of exoplanets, analyze the light of the first galaxies, and test the very fabric of the universe. Missions like LUVOIR and HABEX may find Earth 2.0, a twin world orbiting a distant sun, with oceans, clouds, and the chemical signatures of life. Even more radically, physicists are probing the nature of dark matter, dark energy, and the multiverse. Could there be other universes, parallel realities, dimensions curled in ways we've never imagined? In time, the definition of space exploration will expand from planets and stars to include the most profound questions of existence itself. But with all this potential comes responsibility. We must explore ethically, protect alien environments, avoid contaminating pristine worlds, and ensure that the benefits of space are shared by all of humanity, not just the wealthy or powerful. We must also protect Earth, our only home, for now. Space exploration gives us perspective. From orbit, Earth is a blue marble suspended in blackness. Thin, fragile, and irreplaceable, it reminds us of our unity, our interdependence, and our place in the cosmos. As Carl Sagan once said, exploration is in our nature. We began as wanderers, and we are wanderers still. At Infinity Beyond, we believe the future of space is not just about rockets and planets. It's about dreaming bigger. It's about asking questions no one else dares to ask. It's about becoming something more. The next explorers may not wear spacesuits. They may be AI, avatars, or even code. But their mission will be the same: to seek knowledge, to connect, and to carry the story of Earth into the stars. So what comes after the solar system? The galaxy, the unknown, the infinite, and perhaps our destiny.